In this video, I want to take a look at continuity as it applies to functions of two variables. Now, you may not be too surprised at this point that this looks an awful lot like it did in Calc 1 for functions of one variable. So here's the definition. I say a function, f of xy, is continuous at the point AB if the limit as xy goes to AB of f of x is f of AB. So that is, the limit as you get close to AB is exactly the same as what happens at AB. Right? Now, many calculus textbooks give this definition a little bit differently. They say three things. I think a definition should be as minimal as possible. I don't think you need to say all three things. I think you need to say just one thing here, and the other two are implied, right? And so I would say that just this statement here implies that if these two things are equal to each other, that both of them have to exist. And once they exist, they're equal to each other, right? If you take a look at our textbook, it says that a function is continuous if this, that, and that, right? And just saying this is enough. This implies that f of AB exists, that the function value is defined, right? And that the limit exists. How could the two things be equal to each other if they don't exist? Does one not existing equal the other one not existing? No. So the only way this could actually be equal is if they both existed. So anyway, but when you're looking to see whether a function is continuous or not, if you can show either one of these two, right? If you know that the function doesn't exist, well, it's not going to be continuous at that point because it's not there, right? For functions of one variable, I thought of continuity as being able to draw it without picking your pencil up. And if the function doesn't exist, then you had to at least leave a hole in the graph, and then keep drawing on the other side. Here you might have a hole. Of course, the graphs are surfaces, so you might have a hole in the surface, a little puncture hole. But it still wouldn't be continuous at that point because the limit couldn't equal the function value because the function value is not there. Likewise, if the limit didn't exist, then there's no way that that's going to equal any function value at all. So if you can see either one of those two, you know it's not continuous. A couple of theorems here. As we had with functions of one variable, if you got functions of two variables and they're both continuous at the point AB, then when you add them, that resulting function will still be continuous at the point AB. If you multiply the two functions together, then that new function will be continuous at the point AB. If you divide them, then it's not guaranteed that it'll be continuous, but it's continuous unless you're trying to divide by 0. So if g of AB is equal to 0, then this is not continuous because the function wouldn't even be defined. Right? You can't divide by 0. But otherwise, as long as you're not dividing by 0, dividing two functions will keep them continuous. Will keep the result continuous. And the next theorem, if you have a continuous function g of xy at the point AB, and you have a function just of one variable now, f of x, this is not a typo, this is what I meant, function of one variable, and that's continuous at whatever the output of g of AB is, then the composite function, f of g of xy, is continuous at AB. So the composition of continuous functions is still continuous. Now, I want to show you a couple of examples. First example here is f of xy equals x squared plus xy plus 3y cubed over x plus y. In the video where I'm talking about limits, I actually calculate the limit of this as xy goes to 1, 4. And I essentially do it by just plugging in the 1 and 4. Well, I can do that because this is a continuous function at 1, 4. That is, the numerator is a polynomial. It's a sum of things that are either multiplied together, right? You're multiplying x times an x, you're multiplying x times a y, and you're adding those things up, right? The denominator is also polynomial on x and y. Those are continuous functions, and the quotient of a continuous function is continuous as long as you're not trying to divide by 0. Well, there are places here where you might be dividing by 0. If you're on the line y equals minus x, so if y is equal to minus x here, then that denominator would be 0. But any other spot, you're not dividing by 0, and it is continuous. So in particular, in that other video, when I wanted to know the limit as you go to 1, 4, well, since this is continuous at 1, 4, then the limit equals the function value, so I just plugged in the 1, 4 and found the function value. Here's the graph of that function, and let's click on it to make it live. So this grows rather rapidly, and it's being cut off. It's being clipped, so it doesn't just head off too high. But there's, it's got a y cubed in the top, so as you move in the y direction, this goes up really rapidly in that direction, and then, of course, down really rapidly in the other direction. But you see something's going on here along that line, which, if I can get this rotated, getting it rotated is always a little tricky with this one. Oh, but maybe. So I get the y-axis pointing up and the x-axis going the way we normally have it. Oh, maybe. There we go. Stop. Anyway, there's something that's going wrong along the line y equals x here. On one side of it, it's headed up to plus infinity, and on the other side, it's headed down to minus infinity. And I think it swaps actually over here. On one side, it's going uphill and downhill, and on the other side, it's going downhill and uphill. But yeah, there's definitely an asymptote, a break in the graph along that line, y equals x. No, y equals minus x. Let's go back here now. One more example. This is another one that I showed in a previous video. The f of xy is sine of the square root of x squared plus y squared over the square root of x squared plus y squared. This is ripples. You got the big bump in the middle, and then ripples going out, getting smaller amplitude as you go out. But one of the things that is happening here, there's a discontinuity at one spot. This is continuous everywhere except at 0, 0. Because if you plug in a 0, 0, you're trying to divide by 0, and that's not defined. Right? However, at that same spot, 0, 0, when you plug it in on the top, you get the sine of 0, which is also 0. So this is a 0 over 0, which means the limit might exist. There's a chance that it does. And in fact, it does. The limit as xy goes to 0, 0 here is 1. This is like a sine theta over theta, or sine r over r, however you want to think of it. As you approach 0, 0, this function value gets up to 1 right here. Now, the grapher doesn't even notice that there's a problem at 0, 0. It kind of skips right over it. It doesn't show you that there's a hole right at the top of the hill there. There is a hole because this function is not defined at r equals, not defined at the origin. This is what in Calc 1 we called a removable discontinuity. If the limit existed, but the function value didn't, then you could just assign a function value at that point to be whatever the limit is, and you fill the hole in, and now it's continuous. And so this would be an example of a discontinuous function, but it's a removable discontinuity. It's just a hole in the graph, just at one point. Anyway, there's the notion of continuous functions for functions of two variables.